All right, let's go to page 406, and the first thing you see is one of these. These are actually a little more expensive than you think, so I'd like not to have them broken, but I happen to have two of them. I have one back there. One of them I actually bought, and one of them a student actually bought for me. I thought it was very nice. What this is, it's called a Galilean thermometer, and I haven't actually read enough about this to know if Galileo made one like this. Did he actually make it like this? He didn't have maybe some of the materials. I don't know how he did it, but the way you use this is that you look for the last of these spheres that are floating, and it has the number 72 there. And so the idea is that it should be around 72 degrees in this room. If I were to put it in the refrigerator, then all these balls would actually come to the top like that. If I were to put it in a warm room, then you'd see several of these sinking until the high up here of 80. There's an 80-degree ball up there. What do you think the idea behind this is? What's the idea behind a Galilean thermometer? What does that have to do with this chapter? What do you think, Owen?
All the balls are very close to the density of water, but when the room gets hotter or colder, it changes the density of the water, which makes them, since they're so close, rise.
Okay, so even though if I took some room temperature water and some cold water and I just use a graduated cylinder balance and I tried to find the density difference, I might not even be able to measure it. It might be so small I can't even measure it, but it's enough that these materials actually know that they actually respond to that. As this water here gets colder, it actually gets a little more dense. And as it gets a little bit more dense, it makes these things float in there. I mean, more dense, yeah. These things will actually start floating, and if it gets more and more dense, they'll all start floating. So it is kind of a fine-tuned thing, whoever made these, whatever company makes them. So, yes? You're going to say? Okay. All right, so that's what they start out with. They start out with a picture like that. Now, I won't be spending much time on this because they had it in the first semester, but I do have, I'm going to test. I will probably ask you to convert maybe 3 different temperatures from one scale to another. So let's go ahead and remember that. This is the one I put a star next to because they always give me temperature. Like today, I watched the weather this morning. They always give it to me in Fahrenheit. So the first thing you do, subtract 32.59. Yeah, okay. So anyway, we've done that at least twice for you. The other one's completely opposite. You don't add or subtract first, you multiply. You don't use 5/9, you use 9/5. And then later, you don't subtract 32, you add 32. So that's how you know this one's absolutely the opposite of that. And then here, if you take the Celsius plus 273, you get Kelvin, or Kelvin minus 273 is Celsius. So I think you should go ahead and try a couple of those just to see. What I think you should walk away from class is something like this. The whole world uses Celsius scale except for you, and maybe little pockets, little places here and there. So the whole world uses it. I don't think you should play dumb and say, well, I don't want to use it. I'm not going to use it. It doesn't take that long. I think everybody in this room knows that ice freezes at 0 Celsius and boils at 100, right? I bet more people know that than the Fahrenheit boiling. Raise your hand if you know the Fahrenheit boiling temperature. See, how many of you know the Celsius boiling temperature of water? Okay. All right. So anyway, 212 is just a number. It just doesn't stick with you that long. That's the boiling point in Fahrenheit. And 32 is freezing. Now, and then absolute 0, for example, is 0 Kelvin. It's the only temperature scale that has no negative numbers, and that's why in engineering, science, chemistry, biology, if you did any kind of mathematics with temperature, you had to convert it to Kelvin. And we talked about that in the first semester. Now, so what I'm going to show you, and some of my demonstrations have to do with all this, that temperature is different than thermal energy. So let's talk about the difference there. You'll see me use my hands a lot like this. If I had some water that was at 0 degrees, let's say it's 1 degree Celsius, then the particles would be motion, because if you're above absolute 0, you do have motion. And if you have motion, you have this thing called kinetic energy. So what's the equation for kinetic energy? I look up here. Kinetic energy is 1/2 mv squared, 1/2 mass times velocity squared. So he said, wait a minute, you're telling me that kinetic energy has to do with mass, and what's the proportionality? Let me ask Sophia. Sophia, what's the proportionality between mass and kinetic energy if everything else is held constant? So what proportionality exists between mass and kinetic energy if everything else is held the same? Which one is it? That's right, exactly. They're directly proportional. So if I had a 1 pound ball and a 2 pound ball, and I threw them exactly the same speed, and I let them run into a piece of metal and make a dent in it, then the one that had twice the mass would deliver twice the kinetic energy, wouldn't it? Okay. And well, you've probably heard about this other one, is what's the relationship between kinetic energy and velocity? Let's try that one. What's the relationship between kinetic energy and velocity? What's that one?
It's direct square.
Right, it's a direct square proportionality. So if I had a 1 pound ball and I threw it at 80 miles an hour, and then I had a 1 pound ball and threw it at 160 miles per hour. So what happens if you double the velocity? What happens to the kinetic energy that's delivered? It's actually 4 times greater. Now a lot of people don't realize that somebody actually taught this to you. When you're taking driver's ed, it probably looked like this. When you're going at 10 miles an hour, this is how long it takes you to stop. And then when you're going at 20 miles an hour, it takes you this long to stop. And they didn't even put the numbers in there like I did. They just drew a bar, didn't they? And he said, well, I don't, that doesn't sound right to me, but I'm in driver's ed, so I better pay attention. I want my driver's license. But what they were actually, I don't really doubt whether maybe the driver's ed teacher knew this, but when the speed was doubled, you actually have not twice the kinetic energy, you have 4 times the kinetic energy. That's why it takes you so much longer to stop. Because the idea is to get rid of the kinetic energy of the car. Change it into heat, change it into friction, change it into something, but get that car to stop moving. And that's why it takes so much longer to stop as you go faster. It's kinetic energy. Now, another one I'd like to ask you about to know with this is what if I had I need to tell you another thing. Anytime you hear the word temperature, you should say average kinetic energy of the particles. So temperature is average kinetic energy of the particles. Now I want you to imagine that I have some oxygen gas, this is O2, and I have some helium, and they're both in a balloon, and they're both at room temperature. If you could shrink yourself down and you could actually see the particles, which ones would be moving faster? Or would they be moving at the same speed? And I'll give you a little hint. They're both at the same temperature. Let's try it. Let's try that. Maggie wants you to try it. What do you think would happen? They're both at room temperature, all right? They're both at room temperature. If you could see the particles, would they be moving at the same speed, or would one be faster than the other?
If they were the same temperature?
They're at the same temperature, yes. And temperature is average kinetic energy. Okay, same what do you think? Everybody agree? Well, if you look at the equation, what's the relationship between mass and velocity? If I said they have the same temperature, then I'm actually saying they have the same average kinetic energy. So that's held constant, isn't it? They have the same average kinetic energy. But how can that be? How can they have the same kinetic energy if one of their masses, the mass of O2 is 32, isn't it? Remember the molar masses? The mass of that is 32, the mass of helium is 4. If they have the same temperature, they have the same average kinetic energy, but one of them has a mass that's 8 times greater. If your mass is 8 times greater, tell me about the velocity. It's 64 times smaller. So these particles would be moving 64 times faster than these. They have the same kinetic energy. If I'm light and moving at a faster speed, I have the same kinetic energy as you because you're heavy moving at a slower speed. Is everybody, you okay on this? It's Monday morning. It's actually real physics you're talking about here. You're talking about an equation. So when you hear about temperature, just think about average kinetic energy. You got that? Okay, now, if you had to put your hand in, or you had to have this port on your body or this port on your body, you might say, I might choose that one. Why would you choose 100 degrees rather than 80? If I could shrink myself down and look at the particles, and they're both water, who would be moving faster here? Let me ask Clayton Dunn. Clayton Dunn, in which case will the particles be moving faster here? The teacup of water? And why is that? But actually, this is water and this is water, so the masses are the same. Says what?
Higher kinetic energy.
And why is that? That's right. If you know the temperature's higher, you know the particles are moving, they have higher average kinetic energy, don't they? And so this right here, you know that's hotter because each particle is moving, on the average, faster than each particle here. But I probably wouldn't want this port on my body because there's a lot of it, isn't there? And that's the difference between heat and temperature. Temperature is not heat at all. Temperature has to do with each particle's average kinetic energy, but heat has to do, or thermal energy, has to do with how many particles, how much total energy there is, how much total kinetic energy is there. This thing has more total kinetic energy. One of the questions you might run across in your book is a thimble full of boiling water or an iceberg the size of this building. Which one has the higher temperature? A thimble full of boiling water or an iceberg? Which one has the higher temperature? You said, you're trying to trick me. No, I'm not. Which one has the higher temperature? Mason, what do you think? It does. All right. Which one has more thermal energy? You have to be careful there because both these objects are way above absolute zero, aren't they? There's a huge amount of thermal energy in an iceberg. You don't like to say it, but the iceberg has way more thermal energy than the thimble full of water. Because you got to take it all the way down to absolute zero. You got to get rid of a whole lot of kinetic energy to bring it down to absolute zero. All right, and one more thing, then I'll start some of the demonstrations. I thought it was so neat that my grandson, he's in first grade down here, we were talking about something, and it's not like I just sit around and say, grandson, let's talk about science. I don't do that. It just happens, It just happens. And we start talking about things, and he likes talking about things. He likes discovering things. And he likes all kinds of things. And I like that. He's fresh. They're fresh. Remember you guys used to be fresh? Okay. And so the other day I asked him a question, why do you think that happened? He says, because heat rises. Wow. I was really surprised that a first grader had heard that heat rises. Have you ever heard that? If a first grader's heard it and you haven't, that's sad. Okay? Has everybody heard that? And I myself, because I'm older, a lot older, I've done many things. Like I've painted many rooms in my life. And I can tell you right now, when you paint a house and you get up on a ladder and you paint near the ceiling, it's much hotter than if you paint down here, isn't it? I hate to say this, but a large part of my life, my family's life, we lived in a fairly small house, and we had one window air conditioner. I could not afford central air. We had one loud central box in a window air conditioner. And boy, when we turned that on in the summer, we were in the living room watching TV, and as long as you sit on that couch, you felt great. But then as soon as you stood up, because all the cold air was down here. And so eventually we got ceiling fans. I don't know if you knew this, but ceiling fans have a switch on them. If you pull the switch one way, it'll make the fans go this way, and anything down here, it brings it up, hits the ceiling, spreads it out. And that's what you're supposed to do in the summertime. In the wintertime, though, you're supposed to flip the switch and make it go this way. And then any hot air is here will be brought down. Did you know that? Anyway, a lot of you said, oh, that's ceiling fan. Anyway, so I like what my grandson said, that heat rises. But in physics terms, and I'm telling him this, that's not true. Heat does not rise. Heat always goes from areas that are hotter toward areas that are colder. So if I had something that was hot right here, and I put it in contact with an ice cube, which way would the heat travel? It would go that way. It would actually go down, wouldn't it? So why do we say heat rises? Because when air gets hot, it becomes less dense. And what does less dense air do? It rises and takes the heat with it. And that's why we say heat rises. But heat really always goes from areas that are, watch with my hands, areas at a higher temperature toward what? See that? Think about that. Here's something that's hotter, and here's something that's colder. What happens when these run into these? Won't it make these guys go faster? But won't it make these go slower? That's the whole idea of something cooling off, isn't it? All right, so those are some of the basics. One thing you have to be careful about is, let's do the teacup of boiling water and the iceberg again. The teacup of water has a higher average kinetic energy, that's the word temperature, but the iceberg has more thermal energy. So if I put the teacup and I pour that water on the iceberg, which direction does it go? Does it go toward the area that has less thermal energy into the area of more thermal energy? Well, is that going to happen? Is the teacup of water, is the thermal energy going to travel from the teacup into the iceberg? Or the iceberg has more thermal energy into the teacup? What do you think? Dave, what do you think? So the teacup has a higher temperature, higher average kinetic energy, but actually has less thermal energy than this huge iceberg. So if I pour the hot water onto the iceberg, will the heat go from the hot water into the iceberg that has more thermal energy? Does heat travel from things that have less thermal energy into something that is more thermal energy? Yeah, go ahead.
It goes from the higher temperature to lower.
Right. It actually doesn't matter how much thermal energy two objects have. Heat will always travel from something that is hotter into areas that are cooler, okay? All right, so let me go ahead and I'll do some demonstrations, let you see a bunch of things. We'll get into that tomorrow. All right, so I have, I'll get this ice cubes now. So the first one I want to show you is, this is a neat little thing. I've had some people actually who have patience enough to do this, but this has 4 different kinds of metal on it. It says steel, brass, aluminum, and copper. And then it has these liquid crystal, it's an LCD, a liquid crystal displays, has a little tiny liquid crystal in there. And when they get to a certain temperature, they start showing color, okay? So what you would do is, if you were going to do an experiment like that, you would have a data table already ready, and maybe some kind of a stopwatch, and you'd say, that's block number 1, 2, 3, 4, 5, 6, 7, 8. There's 8 blocks in each one. Now, you have to be careful because it's hard to do all 4 at the same time, but you have to say, let's watch what happens when I put this in there, and tell me if you see any colors appearing. Is anything happening yet? Are they happening? Ooh. Anybody? You see anything?
There's fog on the glass.
Oh, is there? How about now?
Yeah.
All right, so if you want to do this, you could sit there and say, how long did it take before block number 1 for copper started showing color? And then what you would see is that not all metals conduct heat. Metals are great at conducting heat, but some metals are actually better than others. Copper is great at conducting heat, and so is aluminum. Brass, okay. Steel's okay. Anyway, so what you do is you make a little graph called a heating graph, and you say a heating curve. It might be a straight line, but you can do it for all 4 metals. that'd be neat. And then, what you do is after they're all hot, after all 8 bars are lit up, then you take it out and do the opposite and record how long it took to cool off until that block went back to black. So I've had almost every year somebody has thought about this, because I know it's near the end of the year here, we're in now time, but so there's that. I have over here, show you the same kind of an idea. This right here is called a bimetallic strip. Yes?
So what does each block measure on the metals? Does it measure the temperature?
Yes.
Okay.
Good question. Instead of heat, you mean? Yeah, it measures temperature. So when these crystals get to a certain temperature, they seem to change colors. Long time ago, I was teaching at Grimsley, and we had, I thought it was pretty neat. You could actually lay this unit onto an overhead projector. That's before they had document cameras. And you can put it on an overhead projector, hook it up to we don't have one Apple II computer in the whole science department. And so I actually could hook that up, and whatever was showing on the monitor of the Apple II computer would be sent into this LCD unit. And it was actually liquid crystal. There was a problem with liquid crystals. You don't want them to get too hot or they ruin. And so that it has its own little fan. So you put this in an overhead projector, had to plug it in, had a fan to keep it cool. But I thought that was pretty neat technology at the time, that you could actually see what was on the monitor on the TV, up here on the screen. I thought, well, nowadays you take that for granted. But you're right, I have to look into, like right now, they're still pretty green. I think I got them a little too hot. Are the crystals rotating differently? Are they rotating differently, and that's what's giving color? I'd have to look that up. So, all right. So over here, this right here is a bimetallic strip, and it has 2 different kinds of metals that are fused together. So there's one metal here, and there's one metal here. Now, metals heat up at different rates, and they also cool down at different rates. And another thing that happens to things when they get heated, pretty much almost everything I know of, when you heat it, it tends to increase its volume, not mass. It tends to increase its volume, and so it actually metals like to get longer. Anytime, everybody knows that if you're going to build a skyscraper in New York City, you cannot attach one piece of metal and weld it to another. You cannot weld the frame of that building solidly together. You cannot, because in the summertime they have to get longer. If they have to get longer, you don't give them space so long, they're gonna twist and buckle. And so they have expansion joints where it's kind of a floating girder, and have these little places where I'm attached with a nut and bolt thing, but I'm allowed to slide. So if I expand, I get bigger or smaller. At the beach, if you have a bridge, you ever seen bridges that look like zippers? You ever seen that? Okay, so in the summertime, it's hot and everything expands and they kind of close up a little bit. In the winter, they kind of go like that. But nobody falls through unless you have ideal shoes or something like that. And so we have to allow for expansion and contraction. I put in some a laminate floor. A laminate floor, it's called a floating floor. What that means is that you put a piece in there and you hammer it together, you don't nail them together, but it's actually just sitting on top of a piece of foam. And then when it gets to the edge, you just cover it up with what they call quarter round. You guys doing carpentry? If you go home and look at your house, you have this stuff on the very bottom called baseboard. Baseboards that hides where the plaster stops, where the drywall stops. I know what trim now just makes things look nice. And so if I had a floor, what I would do is I'd lay it down and it actually floats. And you wouldn't see the edge because I covered up with this little shoe molding. Well, anyway, in the summer when it gets warmer in the house, those things will actually expand, and that's why when you put it in your room, you don't go all the way to the plaster wall. You always leave a gap. And same thing when you build a deck. If you build a deck on the back of your house, you want to leave a little space between one plank and the other. Number one, the rain goes through it, and number two, you have to leave room for expansion and contraction. So this right here has 2 different metals, and they expand at different rates. So see if you can figure out which one is which. Which one expands at a greater rate? All the ones that pick. Okay, so a little bit, gotta be careful what you're thinking here. Which metal, the one on the top or the one on the bottom expands at a faster rate?
Top.
That's fast. Alright, since they're fused together, they can't get away from each other. If the one on the top expands faster, then it will try to get longer and the other one won't be able to keep up with it. And you might think, well, if you turn it upside down, it'll do the same thing.
Nope.
No, it won't. See that? That's pretty neat. Now you might think, wow, who invented that? I bet they made a lot of money. Not really. How much you think this costs? Very little. So,
2 cents.
right. So they wouldn't make a lot of money. But just I hate this because nowadays almost none of you have one of these on your wall because you replace it with an electronic one. This is called a thermostat. What the heck's a thermostat? Okay, so let me show you what's happening here. Does anybody have like a beach house or a mountain house that still has one of these old fashioned? I call them old fashioned, but I bet you do, right, someone? And you say, how does that work anyway? How does it make sure my house gets either too cold, not too hot? And so I'll take this lid off, you take the lid off, and you say, wow, you can be, there's something behind here? Yeah, and so what they have is, I don't see that one very well, let me use this one. How about this one? You know that thing, that bimetallic strip? What they did is, they put it into a coil to begin with. And now, when the house gets too hot, it'll actually make that coil go one way or another. Now here's the neatest part, and unfortunately, unless you have an older house, you're not gonna see this anymore. This is called a mercury switch. Now, a mercury switch has a little ball of mercury in it, and so what happens is, if it gets really hot, it'll probably, let me see which way is on and off. Let's see, that's hotter. Yeah. Okay. So what happens is, when it goes like this and it starts going this way, the mercury, this way. The mercury, because of gravity, goes down here, and see, these two wires are in that bulb, but they're not touching. But now mercury, which is a metal and conducts electricity, when that mercury goes this way, boing, it'll connect it and the furnace will come on. Then when it gets colder, then the bimetallic strip will go the other way and it'll fall this way and it'll turn your furnace off. Man, they've had this for like almost 100 years. Almost 100 years, that was the neat little thing. That's what kept your house at the same temperature. That's what a thermostat does. It tries to keep the same temperature. So these are, I pass this around, try not to drop it. I have, over the years, I've had many people donate these. You probably just pay somebody, they throw it away, and you say, you get the nice electronic one. But I hate not teaching this anymore because they're still around. All right. Next demonstration is one of my favorite ones. Let's see. Oh, where's my glue? All right. Give me my guinea pig. I'm going to show you one other thing about temperature and heat. Humans are terrible. They are terrible at telling the temperature with their hands and feet. Your hands and feet are terrible at telling the temperature. But your hands and feet are really, really good at telling whether or not you gained heat or lost heat. Terrible at temperature, you're really good at this. So what I'm going to ask you to do, I think you're going to help me out here. I have two black blocks here, and you can either use your finger and just kind of touch it, and just tell me what you feel. Next one. Leave it. What now?
This one feels cool.
Okay, so did I tell you to say that? I did not tell you you had one, right? And so what I'm gonna do is, let me get some ice. And just hang on, I'll be right there.
Just say it's, you're great. Oh my gosh, I need two. Good play. They're putting emergency.
Yeah, I can't believe that thing. Those are-
I'm not doing it. Sorry. Taking steps.
that's only been less than an hour. I just want cold water.
I'll start getting you.
All right, I'll do it later.
That's awesome.
All right, so here we go.
Your teeth are gonna down.
All right, so one more time. Your hand says this one feels cooler, right? So what I'm gonna do is try to take 2 pieces of ice that are kind of the same. Okay, see this? All right, so what we're gonna do is put it about here, and so the one that feels cooler is over here. So let's take a look and see what happens. I know what you're thinking. You're thinking, Clayton, there's no way that would have felt cooler, but every one of you would have said that one felt cooler. So I want to change the way you
Not
think.
now.
I want to change the way you think a little bit, because this right here, even 10 minutes from now, you may or not see any drips of water. Maybe. This will be completely melted, and I can do another one. You say, I don't understand that. Okay, so, yes, what do you think?
I believe it's because that one conducts heat much more efficiently than the other one does.
Say it again?
That one conducts, the one that's melted conducts heat.
It does.
more
As a matter of fact, this one's made out of metal, this is made out of an insulating material. And so this one right here, yes,
So, like, could I try, I mean, not try this, like, can I try to explain why I think?
yes,
No.
Because his body temperature is, or what you feel is relative to your body temperature, so when he touched that one, it probably felt warmer because his body was giving, heat to
this
it.
one felt cool though.
I mean, yeah, that one felt cooler, but when he touched it, he probably felt like, oh, yeah, that one, he probably felt like.
Well said, well said.
He said it felt cool.
Great.
You don't even have to tell me what he said, Craig. I know what he said. Tell me why did he say it felt cool?
He said that one felt cooler.
He did.
Right,
Wait,
because-
Mr. P, how are you gonna get off the desk without spilling water?
It's that little ring will keep it there, but I'm gonna dump it back in there. All right, so it is true, every one of you here would have said that felt cooler. And so that your hand is terrible at telling temperatures. But your hand is really good at telling whether or not heat was gained or lost. This right here, when you touched it, this is made out of metal, and metal's a great conductor. So it actually conducted heat away from his finger. And so he sent a signal to his brain, it's colder, but what you really said is something's taking heat away from my finger. These have been in this room all weekend. There's no way that one of them is colder than the other. If this block were really colder and it was in contact with air that was warmer, then what would the warm air do with the cold block? It would make them reach the same temperature. Both those things have the same temperature. But you said, I don't believe you, because when I touched it, I felt it was colder. It's just because it took heat away from your hand faster. This right here is a very good insulator. It does not take heat away from your finger, so it feels like nothing. Okay, so anyway, the next time you do step from a carpeting to a tile floor, you said, oh, that floor is cold. That's not true. It is exact same temperature as the carpeting and the air. But it's really good at taking heat away from your foot, and that's why you say it's colder. Whenever you see in the winter, they have these signs that says, bridge ices before roadway. And that means if you're a driver, you have to be a little more careful when you go across a bridge. It might have ice on it, even though none of the road had ice on it. You say, what's going on there? Okay, here's the road, ice falls down, and it starts to freeze, but there's some heat in the road, heat gets in there and starts melting the ice. You say, great, but what happens to the temperature of the road when it loses some of its heat to the ice? The road becomes cooler, but it's not gonna stay cooler, because what's a cool road gonna do with earth underneath it? If the earth underneath is warmer and the road cools off, what happens? Heat from the earth does what? Goes into the road. And let's do some more. Let's do some more. But what about a bridge? A bridge, once a bridge loses heat to the ice, all right, what's underneath it? Cold air. There's no more reservoir heat. And that's why the bridge is gonna freeze first. I've seen many times in the, especially in the fall, where there's nothing on the roads, nothing to hurt my driving. And yet I look at somebody's yard in the morning and every blade of grass looks kind of white, or maybe even a twig on the branch is frozen. So what's happening there is that grass is a terrible conductor of heat. And so when it loses heat, it can't get any more heat from the earth. So that water up there just freezes like that on branches. All right, let me get rid of this. Now, I have one more. By the way, I'll have these here, I'll have these here all week. If you said, I think you paid Clay to say that. That's what I have.
I don't think I know.
All right. Now, here's what I need.
And there was one.
Okay, I don't want to hurt anybody. Okay, here we go. I don't want to hurt anybody.
No idea.
All right. All right. Here I have some warm water. It's not that hot. Not that. And I have some cold water. So let me show you. I'm going to try to prove to you again that the human finger and the human hand is terrible at telling temperature. It's really good at telling whether or not you gain or lose heat. All right, you volunteer? All right, put this right finger in there, leave it in there, and put the other finger in there. So you go home and do this at home. It's pretty neat. And we're going to let her sit there for about 20 seconds. And then what I'm going to ask you to do is put both fingers in their room temperature water and be honest, what do you think the temperature of the water is? Are you ready? All right, go. What does this finger say?
I guess it's warm.
And what does this finger say?
It's cold.
See, how can the same water be hot and cold? You take it out now, thank you. So if you go home and do this, one finger will say, that water's hotter, that water is colder. Terrible temperature, it's the same temperature, isn't it? But guess what happened? The finger that was in the hot water, when it went in there, heat went from her hand out, didn't it? It lost heat. She said, it feels cooler. This finger is cold, he put it in there, heat went into her hand, said, that feels warmer. So again, can you believe me that you're terrible at telling temperature, but you're really good at telling heat gain loss? And one of the last things I want to say here, yes?
That's like in the winter when it's like 50 degrees outside, you think it's really hot, but in the summer when it's 50 degrees outside, it's really cold.
There's another story behind that too. How come in the summer, you're sitting out there and it's just really, really hot, and you go underneath the shade of a tree and you say to yourself, well, the air here is much cooler. That is not true. There's no way that air underneath that tree is actually cooler than here. You know why? Because if it was cooler, this air was warmer, and it was bumping into it, it would make that air warmer. And so what happens is, that's a different story. That's another chapter, but you have energy coming in from the sun hitting your face, and you have the temperature of the air also. And so you're getting a lot of energy into your body, and you have energy in and energy out. Now, if I step underneath the tree, the shade, I don't have as much energy coming in, but my body still gives off a certain amount.
So what should we say?
Okay, what you would say is, when I'm standing out in the full sun, I have more, look at me, I have more energy coming into my body than leaves, and it makes my body get warmer and warmer and warmer. When I'm in the shade, I have more energy going out than coming in, and it makes me feel a little cooler. So it's pretty neat, a lot of neat things in this chapter. What we're going to do tomorrow, try to make sure you've read the chapter. We actually started this last week. It's just that some of you haven't been here. We're going to do this thing called specific heat, and we'll do some mathematics with it, and I think you'll enjoy that. So, all right, thank you for, I'll have the thermostats here if you want to look at those. You can see, I've never seen a mercury switch before. There you go. All right, thank you. got it?
Oh, the one we worked with last.
Right from you. Let's see if it's right one.
I'm just wondering which.
Now, so let's say, I don't want the thermostat to come on longer than 80 degrees, so what you're doing, after such a big angle, it's gonna have to get really hot before. Normally, it has to get really hot before it goes on, so if it sits like that, and if it does get that hot, then this will come in contact there with the computer, so every time you turn the furnace on.
So it's supposed to, the mercury's supposed to go right.
No, two wires, oh yeah, to turn off, I wanna turn off the fire, let's just say it starts getting cold. I mean, it starts getting warm, okay, too warm. And then it'll go like this, and the mercury will fall, and then it won't connect to the circuit anymore. And these for about 100 years, such a simple way, it's physics, but a simple thing that people, that overheat the temperature of the house, I'll show you one, this is one of your instruments, not that. For people that at one time had more money. And
Mine's like 10.
so they have a separate one for your air, so if you switch to air, if you switch to, I want the thermostat for my air conditioner, then it'll run off of one of these. Here's one for heat. So you can set this knob or this knob, that's your air conditioning knob, and that's your heat. So if you said, hey, if you switch to winter time, I don't want to use that, I'll switch to heat. This one says cool heat, here, and it'll switch to this guy. So that one is determined. Everything's electronic now. I mean, I like this electronic.
How do the levers do that?
Oh, they have, the factory would have to set it. Now, you're right. The factory would have to have a room where they have all these in there at a certain temperature. And they'd have to say, you know, make sure that lever, you're right. They'd have to adjust that just the right way. This has been used so many times that you can throw it a little bit. It's right. The factory has to make sure that when that's.
Would you like some
it's
pizza?
set.
So the mercury heating up and cooling through these levers.
No.
It's the funniest thing.
Remember that thing, Ben? Okay, so what happens is, I'll try this way.
We can wear different shirts.
All the ones they pick.
I'll toss it to you.
Destroy it. But see if you see this thing moving when you get hot. So it actually, because the dot binder kind of shook, it will actually get longer, or, and it's just a coil already, if you do a coil this way or the other way.
You can make potentially $9 an hour.
Yeah, so this is what makes it work. Mercury just sits there in gravity, says, see, switches off, if I let it cool off, switch on. See the two wires? Right now, they're not touching. They look like they are, they're not. And metal, mercury's a metal, so it can go like that. But right now, there's no way it's gonna turn on for a long time because I heated this up so much. But that's pretty, this is a dual thermostat. And like I said, because a lot of people are getting electronic ones, you lose the physics of 100 years that they used to have done. But anyway, but people like electronics because you can time it, you can set it to come on and off whenever you want. So there people are gonna go to electronics. Thank you. Welcome.
Hey, what are you doing?
What are you doing?
What's up, buddy? Yeah, what are you expecting, Clayton? This isn't new for me.
Yeah.
This actually tracks with my
One line that
personality
is
very
very
well.
well.
This
Like
perfect.
one.
This
What he
this
does.
that one line tracks very well with what you know about me so far. So. Am I wrong?
Is there something you're not?
Am I wrong? No. Me and Sarah.
I feel like I was doing on that quiz, but I feel like I got some wrong.
I told